lab rats and junior lab rats, and welcome to all of our new students. This is going to be your first science lesson. But first things first, you'll need to have your class binder and a pencil handy. If you don't have that, go ahead and pause the video and come back when you're ready. If you haven't already done so, you're going to need to read or skim through the syllabus and the preface section of your binder. You'll notice that your binder's pages are subdivided by section and are numbered accordingly within each section. Go ahead and take a look. We're going to go ahead and familiarize ourselves with our binders now. Once you've skimmed through the syllabus and the preface, I want you to turn to the first page of Lesson 1. If you're not already there, then pause until you're ready. Flip through the pages of Lesson 1 and notice the blank spaces. You are going to often have some blank spaces to fill in as part of your weekly assignment. You will fill in the blanks as you work through each week's lesson while reading, or this week by watching this video, for example. So these pages with the blanks are going to remain in your binder to help you study and prepare for tests. So this is just how you're going to work through your assignment each week. As you flip, you will next find the homework assignment page. Each week, you will either complete the homework page to hand in during class, it'll be right there in your binder, or you will complete the assignment online. This week's homework assignment is to be completed online. And as you notice at the top of the page for your homework assignment, it says online Teacher Ease, and it gives you a date and everything. If you haven't already logged into Teacher Ease, you'll want to pause and do that right now. Make sure that you're familiar with how that portal works. You're going to be getting a lot of information through that this year. So on the back of your weekly homework assignment page, you'll find an image of Rico, our mascot. Each week, you're going to have the opportunity to color him according to a certain theme and turn him in for a prize. If you look at the very bottom of your homework page, it'll tell you what the theme is. It'll also tell you not to put your name on the back side of the page where Rico is. Just put it on the front where it has the blank for name. So if you keep flipping, at the end of each lesson section, you'll find our weekly lab. And sometimes you're going to turn in your lab the following week. It'll be like a homework assignment. And other times you'll complete it during class. So if you would now flip back to the first page of Lesson 1, we're going to look at that first page right here. And did you notice that the syllabus entry for a lesson is repeated on the first page of that lesson? So over on the right side of your page is the first page of your syllabus. For this class is chemistry, for example, and it shows you what the assignment is for Lesson 1. And then if you go and look at Lesson 1 in your actual binder, under the lesson section, you're going to find the exact same text. So this is handy because you know what assignments are turned in each week, and you can look in either place to find them. I also am going to send out a weekly email, and the same exact thing will be there. So just for example, real quick, look at Lesson 1 there on the left, and it says before class, you're going to need to obtain your textbook and your binder, successfully log into your Teacher Ease account, watch Chemistry Lesson 1, How to Science, that's what you're doing right now, and you're going to complete your homework, which is in Teacher Ease, and it's due 8/11, that's the first day of class, at 8 a.m., and you're going to want to review your lesson outline, which is in your binder, Lesson 1. So those are the pages with the blanks that we were talking about. And then it'll tell you what we're going to do during class. It'll tell you what we're going to do for lab. And for this lab, for example, it says keep in your binder. And then we are going to do the test. It'll tell you when that's due. And it'll tell you to begin Lesson 2. So every week, everything is right there for you. You should never even need to worry about knowing what's coming up. So cool. Now that you know what to do, let's get started. Open your binder to the first page of Lesson 1 and have your pencil ready.
Rico presents How to Science.
So what is science? So Google defines science like this: the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. That's a mouthful, so let's break that down. Let's take the word intellectual and substitute mental. And for practical, let's use hands-on. For encompassing, let's go with surrounding. And for systematic, we'll go with organized. For structure, let's go with construction. For behavior, we'll go with actions. Physical, we'll say touchable. Natural, we'll say real. Observation, we'll say watching. And lastly, experiment, let's use the word testing. So let's try that definition again. And let's say the mental and hands-on activity surrounding the organized study of the construction and actions of the touchable and real world through watching and testing. So that's a little less of a mouthful, but more simply, we could just say the study of the natural world through knowledge about the natural world that is based on facts learned through observation and experiment. So science is broken into three main branches. You have your formal sciences over here on the left of your screen. That's mathematics, logic, and statistics. Then you have your social sciences over on the right-hand side of the screen. That's things about societies like sociology and human behavior like psychology. But we're going to focus on the natural sciences. So right there in the middle, you see physical science and life science. Under the physical sciences, we have physics, astronomy, chemistry, and earth science. And under the life sciences, we have botany, zoology, ecology, and genetics. Now, each of these little green boxes, no matter whether they are a bright green or a light green, can be broken down into many, many, many subcategories. Just looking over at under life science, look at zoology, for example. So zoology and botany has to do with plants, and zoology has to do with living things that are animal type organisms. And then under ecology, you've got like how the two interact, and then genetics obviously has to deal with DNA and stuff. Well, just look at zoology. How many different types of studies can there be of living things that aren't plants? My goodness, you could go on forever. You could do biology, you could do medicine, you could do entomology, it's a study of insects. So there's lots of kinds of sciences. What are the big ideas in chemistry? Chemistry is this year, right? So the big ideas in chemistry are going to be atoms, chemical reactions, and bonding. These are the big things we're going to touch on this year. Scientific theory versus scientific law. All right, scientific theories versus scientific laws. When studying science, what's the difference between a theory and a law? This is super important, you guys. This is the kind of thing that shows up on midterms, final exams. I'll ask you about it multiple times during the year. This is one of the things that I want you to take away and keep with you forever and ever, because it's an important thing to understand. So a scientific law tells what happens. It's a fact. A scientific theory tells why it happens, an explanation. So a law is what, and a theory is why. So here's what's important. In this class, we're going to study scientific law and scientific theory. For example, there are multiple theories of origin. In this class, it's a science class, right? So it will be taught from a scientific perspective. Any theories of origin discussed would be scientific theories. So there are multiple cultures and religions that have different theories of origin. But in a science class, you would only cover those from a scientific perspective. So different people hold different personal and religious beliefs, and it's safe to assume that all questions and answers in this class are prefaced with an unvoiced according to scientific theory, rather than, I personally believe that. Why is measurement important? All right, so if you stop and think about it for a bit, you'll realize that measurements surround you on all sides. And guess what? They matter. What are some things that we measure? So we measure length. We measure mass, which is how much matter. So if we go to length for a second, let me just add that it can be the length of an object. It can also it can be like distance as well, right? You can say, what's the length of your path from your house to your best friend down the road? Or you could say, how long is this pencil? Mass is how much matter something has, okay? Matter is stuff. So mass is how much stuff something has. Weight has to do with the effect of gravity on that stuff, the effect of gravity on matter. This is why you can take a an astronaut and send him to space or her to space, and she'll float, right? Because the effect of gravity is less. So her weight is different, but her mass does not change. How much stuff she's made of doesn't change. Area is 2D. So this would have to do with like tiles on a floor. How many tiles would you need to cover a floor? It's 2 dimensions, which would be length and width. Volume is 3D. So that's going to be length, width, height. And that has to do with how much of something fills a given space. And then density has to do with how much mass is in a given space. So if you look at that graphic there, you've got like a sponge, a wooden block, and then maybe a, I don't know, let's say that's a metal block. You'll notice one of them floats most of the way out. One of them kind of half floats, half sinks, and the other sinks all the way. That would be because even though they're all the same size, that steel block or metal block is going to be way more dense than the sponge. We measure time, and we measure temperature. In the United States, we commonly use the imperial standard or customary system. It can be called all these different things. Usually I refer to it as the standard system. Some people call it the English system. This has to do with yards, inches, tablespoons, cups, pints, quarts, gallons, ounces, pounds. What you're familiar with. But in science, and actually in most other countries in the world, the metric system is most often used. And the metric system is based on grams, liters, meters. So if you look at this chart right here, this is a metric conversion chart, and it gives you an example of how the metric system works. So here you have a mnemonic running across the top. It's King Henry died unusually drinking chocolate milk. Unusually just stands for your unit, whether that's going to be meter, liter, gram. And sometimes you'll hear King Henry died Monday, and people just substitute the unit meter in place of the word unit. If you look at the bottom, there's an arrow, and it says if you're going to the left, you're going to divide your numbers by 10 if you're getting bigger. And then it says you're going to multiply your numbers by 10 if you're getting smaller. So I know this probably looks confusing if you've never seen it before, but don't worry about it because we're going to go over it in class a lot. We're going to use it a lot in lab, and it'll make sense to you. It really will, even though you're not used to it because you're used to standard system. So how do you present scientific data? All right, so there's a couple different things to know about data presentation. Data, which is actually a plural word, are the information gained from observing and testing an experiment. Scientists use data to gain understanding and make conclusions. So there's many different ways you can present your data. So for example, you've got bar charts, column charts, graphs, calendars. You even have tables, and sometimes you're going to want to take your number, whatever number you've come out with as part of your data. Maybe it's a measurement or some kind of calculation, and you're going to want to put it in scientific notation, which it says at the bottom. So right there where it says like 7.32 times 10 to the negative fifth, don't worry about that too much yet either. We're going to explain that when we get to it, and it'll make sense. What's a hypothesis? This is super important to understand. So a hypothesis is an idea that can be tested. Requirements for a testable hypothesis. In order to be considered testable, it must be possible to prove that the hypothesis is supported, and you can kind of think of supported like true, although that's really not the best word, supported is. Or it must be possible to prove that the hypothesis is rejected. You can think of that as false, but that's not really a great word. You can think of it as not true, which is maybe a little better, but still not great. You want to think about the word rejected. And it must be possible to reproduce the results of the hypothesis. Whether it was rejected or supported, you should be able to get the same results if you repeat your experiment. Many scientific hypotheses, that's the plural of hypothesis, are proposed in an if-then format because it's easy to design an experiment to see whether or not a cause and effect relationship exists between the independent, sometimes you'll hear the word manipulated variable, and the dependent, sometimes you'll hear the word responding variable. What if a hypothesis is proved or supported? That's the word we're going to go with. A scientist will make sure that she can repeat her process and replicate her results. That's where we were talking about a hypothesis having to have repeatable results. What if a hypothesis is not proved or rejected? A scientist will revise his hypothesis, and often repeat the experiment. So revise the hypothesis. Think about this. You do an experiment and your hypothesis is rejected. So you have to look back at your hypothesis and your experiment and see if there's something you need to change to maybe get a result that is supported. Sometimes they're supported, and sometimes they're rejected. Scientific method. All right. To test a hypothesis, you use the scientific method to conduct a controlled experiment. This is very important. So in the scientific method, if you have a question, you do some background research, and then you construct a good hypothesis, which we were just talking about. Then you test that hypothesis with an experiment, and if that procedure works, yes, you analyze your data, you draw your conclusions. If your results align partially or not at all, you can go back, do more research, revise again, right? And if your procedure wasn't working, then you're going to troubleshoot your procedure, check all the steps, go back, and then you start that process over again. When the results align with the hypothesis, in all cases, you can communicate your results. A controlled experiment is an experiment in which only one variable, the independent variable, is deliberately changed at a time. It's very important that your experiments be controlled. Otherwise, you may not know what is causing the results you see. So your independent variable is what you change. Your dependent variable is what you observe. It's what is being changed. And your controlled variable, or sometimes just called the control, is what you keep the same. You're going to want to be a good scientist. A good scientist engages in arguments using evidence, not emotion, asks questions and defines problems, develops and uses models, plans and carries out investigations, analyzes and interprets data, uses math and computational thinking, constructs explanations and designs solutions, obtains, evaluates, and communicates information. This is how you can be a good scientist. I love this quote, and I wish I knew who made it. I tried to find it, and I couldn't figure out who's responsible for this quote. I definitely don't think that Dr. Frankenstein was a good scientist. He didn't take responsibility for the finished product. When it didn't perform as he wanted it, when it didn't meet his expectations, he turned his back on it. That left the rest of the world to have to deal with it. And here are some other great quotes by scientists. Chemistry states the more energy you put into a bond, the harder it is to break. Chemistry begins in the stars. The stars are the source of the chemical elements, which are the building blocks of matter and the core of our subject. Chemistry ought not be for chemists alone. And I am among those who think that science has great beauty. A scientist in his laboratory is not only a technician, he's also a child placed before natural phenomena which impress him like a fairy tale. Settled science. Lastly, never forget, never, 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 ever, never forget, no matter who says otherwise, no matter what fancy ties or fancy hats they're wearing or how important of a person they are, science is never settled. We hear this all the time. Oh, the science is settled. Untrue. Never settled. And why? Because we're always finding new information. We're always changing our theories. We talked about scientific theories. So just ask these guys. Galileo, he proved the sun was the center of our solar system, not Earth, as was thought before. How about Darwin? He introduced the world to the theory of natural selection, providing the first explanation for the idea of evolution. Joseph Lister applied germ theory to create the concept of sterile surgery. Alfred Wegener originated the theory of continental drift. And Robert Goddard was laughed at for suggesting we could travel to space using a rocket. So who will make the next great discovery? You never know. It could be you.